Alright boys, you know what time it is. It is time to do the FMA practice test. Let's get it. I don't even know which year they decided to reuse for this one, but let us see. Hello everybody, I'm Car, and today we are going to be doing the FMA practice test. It'll be very epic. Dude, it's amazing. The first round of Olympiad is almost over. Just this week and over FMA next week. 2 more weeks and then we are good. So I'll probably just do this FMA practice test. I don't think I'll do that much more stuff. I might do some Amy walkthroughs because I'm probably going to study a little bit for that, but we'll see how it goes. I hope you guys all do well on the A. Hopefully the B is probably going to be before the video is out, so hopefully you guys did fine on that. But I think this is going to be my last one for like the initial Olympiad. I'm probably going to still do Yuzuko and Amy stuff, but we'll see. Alright, why don't we just get into it? Enough talking. Alright, start practice. Welcome to the 2021 practice exam. I do not care, let's do it. Alright, which of the following graphs best shows the velocity versus time of an object originally moving upward in the presence of air friction? Okay, so its velocity should be, so moving upward, right? So upward? So I guess it's just, okay, so for sure we'll have like a constant, or for sure decelerate, right? And then eventually it'll start going downward, and then eventually it'll reach a terminal velocity, right? So this would make sense, right? Because essentially it's going to keep accelerating until its speed cancels out the backwards acceleration, and then it will stop accelerating downward, and then we are good. So D seems to make sense. Or is it E? No, E doesn't make sense. Why would it? There's no way the drag force can be more than the. Yeah, for sure not going to stop at 0. Does it ever hit the ground? I mean, I'm assuming it doesn't hit the ground, right? Yeah, it wouldn't be a gradual stop, so yeah, that should be fine, okay. A 3 kilogram mass moving 30 meters per second to the right collides elastically with a 2 kilogram mass traveling at 20 meters per second to the left. After the collision, the center of the mass of the system is moving at a speed of, okay. So for these ones, you don't have to think at all. It's literally just the, you just find the center of mass speed does not change. So we can just do 3 times 30 minus 2 times 40 is 50 divided by 5, and you get 10 to the left. Okay. Oh, sorry, 10 to the right. Alright, ball 1 is traveling in the positive x direction, strikes an equal mass ball 2 that is originally at rest. All of the following must be true after the collision except. So it didn't say whether it's elastic or inelastic, so, like, it could be either, so final momentum is for sure true, so this is right. Total kinetic, that's not necessarily true, I mean, is that it? Okay, yeah, I guess that's it. B. A satellite is following an elliptical orbit around the Earth. Its engines are capable of providing a one-time impulse of a fixed magnitude. This seems familiar. Okay, I don't remember which year this is, though. In order to maximize the energy of the satellite, the impulse should be what? Okay, so essentially, like, you want to do the most, you want to have the greatest, so impulse is going to change your velocity by a fixed amount, right? So, essentially, you want to change your velocity by the greatest percentage. And essentially, like, at perigee, it's going to be moving the fastest, right? Because, like, conservation of angular momentum. So, you basically don't want to do it here, right? Because then your velocity is really high, so the fixed change in velocity is going to be pretty small. So you probably want to do it at apogee. And you want to do it in the same direction as your velocity, so you increase it. So, it should just be B. 2 masses are attached to pulleys. I think I will need scratch paper for this one, but let's see. All surfaces are frictionless. If the masses are released from rest, then the inclined plane will. All surfaces are frictionless, so there's a frictionless thing here. Why would the thing move? Because the. What? Why would it move? My brain is frying. What? Seriously? Why would it move? I don't get it. Yeah, I don't think it would move, right? Because, like, the center of mass has to stay in the center. Like, how could it move left and right? I'm, like, 200% sure it doesn't move. Right? Okay. Yeah, why, like, the mass is only vertically accelerating, right? So there's no reason why it would move left or right, right? I'm pretty sure. Okay. Yeah, because, like, basically tension. Yeah, so, like, the horizontal forces for sure cancel out, so we should be good. A packing crate. Okay, I think we'll finally need scratch paper for this one, but a packing crate with a mass of 115 kg is slid up a 5-meter long ramp, which makes an angle of 20 degrees, okay? Alright. Frictional force of 4 times 10 squared resists the motion. So if it starts at rest, then what is the speed at the top of the ramp? Alright, this should be fine. Okay, so essentially we got our ramp. The ramp is 5 meters long, so I'm assuming this is 5 meters, right? And you have a block, and you have a force. So essentially the force is just 600 newtons upward, like parallel, right? And then what are the speeds? So essentially you could just use the big 5 one where it's like Vf squared minus V0 squared over or is equal to AD, right? So if our A, what is our A, is just 600 over 115, right? And then our D is 5, right? It starts at rest. Yeah, if it starts at rest, it is 0. So it should just be root of 2 times 600 over 115 times 5. Square root of 2 times 600 over 115 times 5. 7.22, which is C. Very cool. The car has an acceleration of a0 and a minimum acceleration of negative a0. The shortest possible time for the car to begin at rest, then arrive at rest at a point distance d away is, okay. So, if you have a constant acceleration, you're basically going like that, and you're going like that, right? Or, in other words, if we do the velocity versus time graph, then it's essentially like a triangle, right? You have constant acceleration as a slope, constant acceleration there, and the distance you travel is the area under the curve, right? Okay, so essentially you want the area, and this should be, or the slope here is a0, and the slope here is negative a0, right? So, this should be like t over 2, right? Basically, for the first half of the journey, you want to be accelerating as much as possible so you get as much speed, and then you decelerate as quickly as possible, as late as possible, to slow down to a stop. Okay, so essentially, if this is t over 2 and the slope is a0, then this should be a0 t over 2, right? So the area of this triangle is going to be t a0 t over 2, 1/2, remember, 1/2 base times height, and that should give us a0 t squared over 4, right? And that is equal to d. So if we want to solve for the time, we get d, 4d over a0 is equal to t squared, so t is equal to 2 root d over a. Very cool. So that is E. Nice. Is that right? Am I not trolling? I'm probably not trolling. Hopefully I'm not trolling. I don't think I'm trolling. Okay, we should be good. Alright, disk of radius r rolls uniformly without slipping around the inside of a fixed hoop of radius r if the period of a disk motion around the hoop is t. What is the instantaneous speed of... Is there any gravity nonsense? Rolls uniformly. I mean, I'm assuming that there's no gravity. Yeah, that would not make sense. Okay, well, first we had to find the speed, right? So essentially the center, the period of the disk motion is basically how long it takes to get back to its center to get back to its original position, and the center has a radius r minus r, so the distance it travels is 2 pi r minus r. Alright, and then once you find the distance it travels, then its velocity is just over t, right? So the velocity of the center is over t, and then the instantaneous speed, so the instantaneous speed of the center is this, right? So that means that the instantaneous speed of a point over there is just going to be times 2. Because essentially, like, if you have this, right, the angular velocity about the pivot point, like the point that is touching the bottom, is, like, constant throughout, right? So essentially, you just know that the ratio of this r to the total r is 2, so you multiply by 2. Very cool. And that should give us D. Very nice. A uniform stick of mass m originally on a horizontal surface. Okay, one end is attached to a vertical rope. Okay, I remember this one, but I remember I did not, I trolled on this one sometimes, so let's see if we can get it right this time. Which pulls up with a constant tension force F, so that the center of mass of the stick moves with acceleration a less than g. The normal force of the ground on the other side of the stick shortly after the right end leaves the surface satisfies what? Okay. Alright, so we got F over here, we have like mg over here, and we have like n over here, right? So essentially ma is equal to F plus n minus like mg, right? And then, what else do we know? We know some torque stuff, right? Do we know any torque stuff? Well, I mean, there's some acceleration nonsense. Why don't we do acceleration about this angular acceleration? So, we basically have, like, what? Uniform stick. So, let's just say this is a pivot point, then the moment of inertia is 1/3? Yeah, 1/3 ml squared, I guess, which is not... Okay, well, times alpha is equal to F times L minus mg L over 2. And alpha is just A over L over 2, right? So it should just be 2A over L, alright? So we have these two equations. We could probably cancel out this nonsense. Alright, so essentially you want to get rid of F because F is an unknown, right? So essentially we get 1/3 ma is equal to n minus mg over 2, right? So essentially, n is equal to 1/3 ma plus mg over 2. Hopefully I didn't troll, but that suggests that acceleration is greater than 0, so but it's less than g. So it should be B, right? B would make sense to me. So we're gonna go with B. Alright, so essentially we got a graph and shows the acceleration versus time of an object originally moving upward in the what? Isn't this literally what we just did? Hold up, what's the difference of this? What? Oh, acceleration versus time, not like position. Was the first one position? Oh, velocity. Yeah, that should be fine. Okay, so this is a different. Alright. Okay, so acceleration is like constant downward, right? Until but not it. So I guess it is more downward, right? So essentially it is like very downward, and then once it's turned around, then it is very upward, and eventually very upward, and that acceleration goes down over time, right? So wait, what? In the presence of air friction, so originally moving upward, so it's for sure down originally. So as it slows down, right, the acceleration gets less extreme, and then as it gets faster, it still gets less extreme. So D seems legit. There's for sure not like a instantaneous thing, right? Because at some point it's like, okay, wait, is there? No, because it should keep accelerating downward until a certain point. Yeah, I think D makes the most sense here. All right, and it for sure should have an asymptote at the end because like you got like what do you call? You got terminal velocity. Wait, does this make sense though? So as you're going up, your speed is decreasing slowly and steadily, and then eventually you get to 0, in which case it's just purely 9.81. Oh, wait, yeah, it should have a asymptote of 0. That does, yeah, okay, E makes so much more sense, because there is terminal velocity, so these two are for sure not right. Wait, none of these are right. It's for sure E, because at some point you gotta stop accelerating. Okay. Wait, seriously? None of these have an asymptote of 0 except for the last one? Alright, I'll take it. A light, uniform, ideal spring is fixed at one end. If mass is attached to the other end, the spring oscillates with okay, I see. And if another spring, okay, so it is put in between. Alright. So basically the way you approach these problems is like, okay, so for the first one, if you have a spring with spring constant K, and you like stretch it a tiny bit, like let's say it was stretched by delta X, then the restoring force is just K delta X, right? However, if you split it in half, basically, like, a thing you have to remember is if you attach two springs in series, you're basically taking the harmonic average of their k's, right? So essentially, by splitting it in half, you basically double the spring constant. This is something you could derive. It's not that hard to derive, but it is an important thing to know. If you split it up, it becomes twice as much, so there's 2k as well. Alright, so if you move it slightly over by delta x, let's say, then the restoring force is 2k times delta x from this guy and 2k delta x from this guy. So it is overall 4k delta x, right? So essentially the effective k is duplicated 4 times. So that is pretty epic. Is that right? Yeah, that makes sense, right? Yeah, that makes sense. Alright, so if our k is multiplied by 4, then, well, okay, so basically like the angular frequency is root k over n, right? So essentially if you multiply your k by 4, your omega is going to be multiplied by 2, which means that our answer is D. Very cool. Alright, so a group of students wishes to measure the acceleration of gravity with a simple pendulum, right? So T is equal to 2 pi root L over G. Okay, so that is an important thing to know. And essentially, we want to find the computed. So essentially, the only thing it's testing here is the uncertainty, right? So basically, the propagation equation that you should know is what? What was it again if you take square roots? Oh, square root's kind of nasty though. Well, okay, so essentially like if you divide, so first we'll do the division. Let's solve for g first. So g is equal to t over 2 pi, 2 pi l squared. No, what? 2 pi, okay, I'm good at this game. 2 pi over t squared. There, that is what we get for g. So essentially if you square something, it multiplies its thing by 2. Basically, that is just what you gotta remember. Basically, like, it's pretty easy to derive, like, these rules just using, like, derivatives, right? So if you take the derivative of t squared, you get, like, 2t dt, right? So essentially, you just multiply by 2. So essentially, we want to take these 2 pi squared times the square root of, like, 0.05 over 1 squared plus 2 times 0.1 over 2 squared. That is just the equation, and if we do this out, pi squared times square root of 0.05 squared plus 0.1 squared, you get 4.41. That's not right. Hold up. Did I write it right? Okay. So then, in order to get the actual, then you're supposed to. Oh, wait. Huh. Okay, what is it like this? That's 0.11, right? And then we times 2 pi. Okay, so in order to get this, you had to multiply by, like, L over T, because this is a relative uncertainty, right? Like, you basically have, over X. So if X is equal to Z, then essentially sigma X over X equals sigma Y over Y plus squared root. Okay, so basically you had to multiply by X. Alright, that makes a bit more sense. Okay, so we'd have to multiply this whole thing by over 2. But even then, that doesn't really make sense, does it? Oh, L over T squared. Okay, so over 4. Oh, okay, there we go. That's what I was doing wrong. I gotta multiply by L over T. Okay, so that should just be D. Very nice. Alright, finally, that took way too long. Okay. A massless cable of diameter 2.541 inch is tied horizontally between two trees, 18 meters apart. Alright, seems legit. Okay, so essentially, they stand in the center of the cable, giving tension 7300. Cable stretches and makes that. Alright, so essentially it is delta L over L. Okay, so the stress is not hard, right? Stress is just force per unit area, so that's just 7300 over what? Like pi times 2.54. Oh, we should probably do in meters. 0.0254 over 2 squared. And then the fractional change in length is just going to be this is going to be a really massive number, but essentially the change in length should just be like L over, wait, so what is L originally? Oh, so, okay, so it is 9 over sine, like what? No, cosine. Cosine 1.5 times 2 minus 18. All over 18, and that is your strain. And then we just want to find the ratio of stress to strain, so it's just this over that. Alright, let's do it. 7300 over pi over 0.0254 over 2 squared. Alright, that is the first part. And then we divide it by 2, or we could just do 1 over cosine 1.5 degrees minus 1. Okay, 4.2 times 10 to the 10 is what I got, so I guess we're going with E. Very cool. Is there anything I did wrong anywhere? I think we're good. Yeah, we should be fine. Alright. 3 identical masses are connected with identical rigid rods and pivoted at a point A. If the lowest mass receives a small horizontal push to the left, it oscillates with period T1. If it ascends, instead is pushed into the page, it oscillates with period T2. Okay, so into the page is kind of easy, right? Because the only one that's moving is the bottom one, in which case the moment of inertia is ml squared, right? Oh, wait. And then I guess it's pretty easy to do the other one too, right? Because then the other ones are just going to give a moment of inertia overall of 3 ml squared. And I forgot the equation exactly, but we could just derive it real quick. So if you have a pendulum and the center of mass is here, then essentially the torque, so I alpha, is equal to like mg times like r, which is the distance from the pivot to the center of mass, times cosine theta, which is the displacement. So essentially the k is basically just like mgr over I, right? So then our k, no, our k is gr over I, so what? How does it work? So a would be like kx, right? So, or ma would be kx. So this is basically the value, right? So you just do the period is just going to be I over mgr. And mg and r all stay the same, so our I just multiplied by 3, so it should just be c, root 3. Very cool. A satellite is in circular orbit around the Earth. Over a long period of time, the effects of air resistance decrease the satellite's total energy by 1 joule. The kinetic energy of the satellite, let's see. So satellite's total energy decreases by 1. So I'm assuming that if it's over a really long period of time, it'll still remain in a circular orbit. So that basically means that in a circular orbit, your kinetic energy is equal to, well, your centripetal acceleration is equal to v squared over r is equal to g me over r squared. So eventually v squared is just equal to gme over r, which basically means that your kinetic energy is just 1/2 gm em over r. Okay, and then your potential energy is just equal to negative gm em over r. Alright, so if your total energy, which is going to be negative 1/2 gm em over r, decreases by 1, right, then essentially your kinetic energy is going to be what? Okay, so essentially your kinetic energy is 1/2 a, and is negative a, or negative total, and your potential energy is positive 2a, right? So if you decrease by 2, that means your kinetic, or if you decrease by 1, your kinetic energy increases by 1, and your potential energy increases by, or decreases by 2, right? Yeah, okay. So it should increase by 1, so A. Very epic. Alright, an artificial space station produces artificial gravity by rotating with an angular frequency of omega. Consider working in the reference frame rotating with the space station. In this frame, the astronaut is initially at rest standing on the floor facing in the direction that the space station is rotating. The astronaut jumps vertically relative to the floor and with the initial speed of less than that of the speed of the floor, okay. Just after leaving the floor, the motion of the astronaut relative to the space station floor is what? So it is an artificial gravity, right? So, how does that work? Okay, I'm pretty sure like once you jump, like he doesn't have any acceleration, right? Like there's no gravity acting on him, there's no forces acting on him, so there shouldn't be a component of acceleration. But he should reach the floor again. Let's see. But it just does say he have a component of acceleration. Really? But how? What's causing the acceleration then? Well, okay, so basically, like, the guy is moving with the floor, right? So, like, let's say he is here, and the floor is moving that way, then when he jumps, like, he'll move upward and this way, right? So, essentially, he'll eventually hit right there, right? Oh, so it's relative to the floor. I mean, it should be downward, right? Like, how else is he supposed to get back to the floor if he never goes back to it? So, I mean, basically, you can see, like, it's going to be a straight line, but, like if you have a straight line here, right, the floor is moving like this and he is moving like that. So this would be a 45-degree angle if he was moving if he jumped at an initial speed equal to that of the floor, but he does not, so it's less than a 45-degree angle. Wait, what does that even mean though? Oh, so that means this would be a 45-degree, 90. Oh, okay, I see. So it's for sure one of the directed to the floors. So I guess there are 3 options. So let us calculate this. So let's say the floor is moving at omega, and this is a 90-degree angle, right? Okay, well basically theta is equal to tan inverse of v r over omega, right? No. V over r omega. Okay? Then essentially the amount of like distance the floor needs to travel is going to be just, or the time it takes for the floor to travel to that point is going to be theta over omega, right? And the amount of time it takes this guy to travel there is just going to be what? Or sorry, this should be like 2 pi, or no, sorry, pi minus, or no, pi over 2 minus? Yeah, okay, because, yeah, it's 90 minus that. Wait, what? No. So it is like 1, so it's like pi minus 2 times pi over 2 minus theta. Okay, that was nasty, but essentially this just translates to 2 theta. Okay, so this is 2 theta omega. Then what is this length? Then this length is just like, this is theta, this is theta. So that's just going to be r times 2r, what, sine theta? Okay, and this is going to be over v, and that's going to be over omega. So let us see which one is bigger. 2 tan inverse of v over r omega, I guess, over omega. And tan inverse, okay, so I guess that means this is v over r omega, and that's 1. Wait, but that's nasty. Go on. What? How do we quickly figure out which one is bigger? I do not know how to approximate this very well. Fine, I guess we take the ratio. Does that help? So if you take the ratio, then it's just like theta, theta over sine theta r omega, and then that's v. So we just need to figure whether this is less than 1 or not, but I don't know. Okay, let's just try plugging in 45 degrees, right? So it'll be like pi over 4 times v over r omega. So v over r omega is just equal, so it's 1. Pi over 4 over root 2 over 2. See that? Okay, so that's slightly bigger. So essentially, the points take longer to get there, which means that he should land in front of his original location, right? So I am assuming, well, let's just test it with a smaller thing. Let's just say it's half, right? So if it's half, wait, no, it should be like 1 over root 3, the ratio. In which case it is 30 degrees. So we'll do like pi over 6 over what? 1 over square root 3 over sine theta, which is 1/2, right? Which is less than 1? Uh-oh. What? Okay, so pi over 4 is above, wait, what? So pi over 6. Sine of pi over 6 is 1/2, so you multiply by 1/2 and you divide by root 3. Oh, no, no. What? What? Why? Okay, did I write this wrong? Okay, so 2 theta over omega, that makes sense, alright, and 2 theta, yeah, that's what it is, right, and over omega, okay, and then 2r sine theta, which gives you r sine theta, so that's this, 2 times it, and then divide by v. It's root v squared plus r omega squared. Oh god, that's nasty. Oh my god, that's nasty. Hold up. What? Okay, well, let's just assume that they're equal, so I guess now it should work. So, instead of v, it should just be root v squared plus r omega squared. So this should be root 2v, right? Yeah, and then that's just equal to that, so it should just be times root 2. So pi over 4 over square root 2, and then times square root 2. So I'm assuming that should be fine for the rest. So it'll be like 2v if it was the other case. So pi 6 square root 3 times 2, or times v over rw. Well, okay, so times 2 for the sine, and then we had to multiply by another 2. And right, okay, so it should be like, it takes longer for it to get there, so it should be, he lands in front of his point. So, B. Alright, seems legit. Alright, I remember that this one was wrong on the answer key or something, but I forgot what the answer was. A stream of sand is dropped out of a helicopter, initially moving at a constant speed v to the right, alright? It suddenly turns and begins moving at constant speed v to the left. So, neglecting the air resistance on the sand, what is the shape of the stream of sand as viewed from the ground? Okay. The basic idea is that, like, when it's moving right, the sand it's dropping is also moving right with it, right? And, relative to the helicopter, it looks like it's just a straight down drop, right? So if it looks like a straight down drop from the helicopter, wait, no, that doesn't make sense. Wait, does it? Wait, should it just be like a straight line down then? No, what? Well, yeah, it should be D, right? Because, like, from the perspective of the helicopter, like, it looks like it's just going down, right? Like, if you just take everything out of the picture, like everything is moving with the helicopter, then yeah, it makes sense that it would go straight down. So, like, at any point, it should look like this. So D seems legit. Very epic. A mass M is attached to a thin rod of length L so that it can freely spin in a vertical circle of period T. The difference in the... Okay, fun. Alright, so essentially you have L, you have M, and you have what? ML, I guess, but how do you do this quickly? How do you know what the speed is even? But then the speed is different, right? If it's a vertical circle, because gravity is a thing. Huh. Oh, you're just supposed to use conservation of energy. Oh, I guess you are. So essentially, the bottom guy's kinetic energy, let's just say, is like 1/2 mv0 squared. Okay, and the second guy should have is equal to 1/2 mvf squared plus mg2l, 2mgl. Okay. Then if you have 2mgl, what does that mean? Well, okay, so the tension should be mg plus like mvf squared over r, right? Or minus. Yeah, minus. Okay, so at the top the tension should be minus mvf squared over l, and then at the bottom it should be plus. So plus mv0 squared over l. Alright, so that is the tension difference, and if we subtract the two, we basically get, when it's at the bottom, it should be a lot faster, and it should need a lot more tension, so it should be mv0 squared plus mvf squared over l, right? Wait, how do you get the t in it? What? So at the bottom, it should for sure be that, okay. Okay, so we have the sum of it, but we don't have the, okay, how do you get the... Wait, is it a... No, it's not, sure not a, wait, is it? Is it actually, is it a dimensional analysis problem? Wait, no, there's a lot of things that have the same dimension things, so that is probably not dimensional analysis. What does period have to do with anything? Huh. I feel like it should not involve period at all. So essentially we could set this to equal to, it could be mvf squared squared, or 2 times that, plus 4mgl over L. Somehow we need the mvf squared. I mean, I'm tempted to put 6mg, but why though? Why does that matter? Why is that right? So mg minus the amount of centripetal acceleration you need, that's correct. And then mg plus the amount of centripetal acceleration you need. Okay, you know what? We'll come back to it. I'm not sure what how you're supposed to do that one yet, at least. Okay, raindrops with a number density of n drops per cubic meter and radius r0 hit the ground with speed v. Okay, the resulting pressure on the ground from the rain is p0. If the number density is double, drop radius is halved, and speed is halved, the new pressure will be. Okay, so n drops per cubic meter, and you have speed v. Oh, are we just supposed to? Okay, let's just say. Okay, so let's just say the mass is like m, right? So that means like m kilograms per cubic meter. Oh, so the mass is basically proportional to the radius, right? So 4 pi r0 cubed over 3, so n r0 cubed. So that's how much mass per cubic meter, right? And then times the speed, right? Which is going to give you, this is going to give you the impulse per second, right? So it's going to give you kg meters per second, and then per second, right? So the impulse per second. And that is just the force. Oh, but then per cubic meter. So we have kg is this thing per cubic meter, right? And then you multiply by m over s. So now you get like, okay. So if you do times v0, that gives you like the that gives you the mass per meter squared per second, right? So this is mass per meter squared per second, and then if you multiply by v0 again, then you get impulse per second, which is the force per meter squared. Okay, so this is just your pressure, and if you just plug in the double halve, so that's like 1/4, and then halve the speed, so that's another 1/4, so that should be E, 1/16. Very cool. Alright, a spring is stretched to double its unstretched length, has a potential energy of U0, okay? If the spring is cut in half and each half spring is stretched double its unstretched length, then the total potential energy. Okay, so we did this before, so you have 1/2 like x times k times like, I don't know, x squared. And then if you do half, your k is going to be multiplied by 2, and then your x, the change in x is now like half, right? Because by doubling it, like, its original length is L, so that's, by doubling it, you add another L to stretch it, right? So now if original L is L over 2, then if you double the length, then it's stretching it by L over 2, so this should be x over 2 squared, and then you multiply by 2. So, I mean, from this you could clearly see that it's literally the same, right? It should be just, if you use E0, right, this all cancels out, and you get the same answer. So, answer should be C. Alright. A ping pong ball with a mass m is placed on the ground with initial velocity v0 and 0 angular velocity at time t equals 0, the coefficient of friction between ping pong ball. So we basically want to find out when it starts rolling without slipping. Okay, so basically we have friction over here, right? And we have, that is literally the only force that is going on. So the frictional force is mg mu, and that is equal to ma, right? So your A is literally just equal to g mu. Alright, then what about our angular acceleration, right? So our I, it's a hollow spherical shell, which means that our moment of inertia should be 2/3 m r squared. Okay, very cool. And then times alpha should equal to fr, right? Because that is the only torque on it. And alpha is just equal to a over r. Is it? No, there's a difference. Okay, so this is just equal to like mg mu r. So this is just going to be g mu r out. Wait, what? Okay, so it should be g mu over r. Okay, so our alpha is g mu over r, or 3/2 g mu over r. Okay, so essentially it starts rolling without slipping once alpha is equal to a over r. So essentially we want our A, which is decreasing because of friction. So we basically want A minus G mu T is equal to R times like what? Alpha T, right? Which is 3/2 G mu over RT. And then if we just solve, we basically get 5/2 G mu T. So our T is just equal to 2/5 A over mu G. Sorry, what? Initial velocity. Oh, sorry, this should be initial velocity. Okay, that was what I meant. V0. Alright. And that is just A, very cool. A small hole is punched in the bottom of a rectangular boat, allowing water to enter the boat as the boat sinks in the water. Which of the following graphs best shows how the rate of water flow through the hole varies with time? Okay, so so the boat is sinking. How the rate of the water flow through the hole varies with time. Okay, my question is, why would the water level outside the boat be different from the water level inside the boat? There's really nothing preventing the water levels from being the same, right? So shouldn't I guess the rate at which the boat sinks increases over time though, right? How do you do this? There should be a smart way to do this, but I'm not sure what it is. Alright, so what options do we have? I'm assuming it should go down to 0, right? Because once the boat is fully sunk, it shouldn't keep flowing through the hole. Oh, okay. So essentially what I think is that like the distance between the water level and the water level outside and the water level inside always stays the same, right? Because essentially, like, your boat always wants to be, or like, the water displaced has to be enough to support the weight of the boat, right? So essentially, it'll keep moving down to keep this height the same, right? So then I guess the question is, well, that means it should always be a constant rate, right? Well, I mean, there is more water inside, so shouldn't the rate go up because the difference in height? Yeah, because I'm pretty sure like the amount of water that's flowing in should be equal to the height difference, right? So I think it should be just A. Not entirely sure. Okay, coefficients of static and kinetic friction between a ball and a ramp, and essentially at the angle of the ramp. Okay, so why don't we just solve this, right? So I think the main thing you have to know is that like tan theta is equal to mu s, right? So the critical angle at which the it stops rolling without slipping. It stops rolling without slipping is tan theta, right? So at some point it'll stop rolling without slipping, and then once it reaches that point, then once it's just like what? Then it'll just be like kinetic energy, right? Kinetic friction. So once it is past that point, okay, let's just say before that point, then what is the rotational acceleration? If it's rolling without slipping, then you basically have mg, you have what? Mg sine theta minus mg mu cosine theta is equal to ma, and essentially we have I times mg mu cosine theta is equal to, this is equal to I alpha, which should equal I a over r. But if it's not this, then it's just rolling without slipping, in which case just mg mu cosine theta is equal to I a over r. This is the only equation that matters, right? In which case, in terms of the angle, is it just in terms of cosine, I guess? Wait, is it always just in terms of cosine then? Like, how does it matter? How does this matter? Huh? Well, yeah, why would the other thing matter? Let's see. It's only asking for rotational acceleration, right? So, well, okay, think about it this way, right? At 90 degrees, the rotational acceleration is for sure 0, right? It's not moving anywhere. At 0, it should also be 0. So, wait, seriously? The only one? What? Dude, why would a ramp at angle 0 not have a 0 thing? And why would a ramp at angle 90 not have a 0 thing? That doesn't make sense. Okay, so C, I guess, is just the answer, straightforward. We don't have to think about it too much. Alright. C. But there is a difference, not just cosine, so we have to think about it a little bit. Technically we don't on the actual thing, but we should probably do that. Whatever, let's move on though. It's pretty clear that that's the answer. A mass is attached to one end of a rigid rod, while the other end is attached to a fixed horizontal axle. So initially it's like this, and we got that, and there's an axle there. Okay, so how does large angle approximation matter? So I guess when you go like, as your angle increases, your it diverges from the small angle approximation by your theta is a lot bigger than sine theta, right? So that basically means that your force is going to be, well, it's basically that your force is going to be, what? I mean, basically saying that your force is going to be smaller than you expected it to be, right? Wait, let's see. So pi over 4 over square root 2 times 2. Yeah, so I guess, like, the small angle approximation underestimates the force, which means that your period should be a little bit bigger. Yeah, I think it should just increase, right? Like, b. Why would it approach a finite constant, I guess? Yeah, I'm just gonna go with b, because, like, when you increase your theta beyond, like, small angle, it'll overestimate it a bit, in which case the period should be a bit smaller. I mean, bigger. But eventually it'll start, like, going in circles, right? And then it'll keep going down, because the faster you do it, the faster. Oh, okay, so I guess E is the answer then. Okay, so circles are a thing. That makes sense. Alright. Alice and Bob are working on a lab report. Alice measures the period of a pendulum to be that. Okay. Alright, so if you keep Alice's and ignore Bob's, then your uncertainty is 0. So 1 is going to be 0.008. Alright, that's pretty decent. If you average the two, then you're basically taking, like, x plus y over 2, in which case your uncertainty is just square root of 0.008 squared, plus, what, 0.016 squared. And that is 0. That, and then divide by 2. So, what? Y is over 2, over 2. What? Why is it not showing me my answer? Okay, 0.0089, so it's slightly bigger. And then perform a weighted average of Alice and Bob's results. Weight Alice's 4 times more. So, in that case, you multiply this by 4, right? And is that it? Oh, and then you divide by 5, right? Well, let's close all this nonsense. Divide by 5. Oh, well, the 4 should be in here. 4 times 0. And that is 0.007. 0.0072. Okay, so clearly 3 is the best. Method 2 has the highest. Alright, so B seems legit, and one more we had to do, and we should be good. Alright, this boy. Mass M is attached to a thin rod so it could spin freely in a vertical circle with period T. What does the period have to do with that? I don't get it still. What? Okay, so L, M. And you got L, M. Alright. Okay, so let's just say L stays the same. Then your period should be directly proportional, or inversely proportional. You know what? Let's just go with C. I don't think we have enough time. I don't know how to do that one. Alright. Submit this boy. Alright, 22, not bad, not bad. Alright, so this one's right, that one's right. Alright, 6. What? How do we get this one wrong? What? So, it's like that. Oh, I'm so bad. I forgot to do gravity. Okay, so 10 cubed, 600 minus, we got to do minus 115 times 10 times sine 20 degrees, right? And then we do all that other stuff. So it'll be 600 minus 115 times 10 times sine 20 degrees. So that's 206, okay? And then we do square root of 2 times that over 115 times 5, and we get what? 4.24, is that correct? Okay, I think it was A. We'll check. Wait, actually, are the solutions linked? Oh, okay, they are linked. What, I trolled that one? Okay, well, oh, I didn't even notice. Oh, I got it backwards. Proportional to greatest change of that is when speed is the largest possible. What, why? Speed is the largest possible, and then you increase it more, but then what's the percentage not being as much? Oh, because you're changing. Oh, because a lot of it is in, like, your potential energy, so the percentage doesn't matter as much. You're trying to increase your total energy, right? Yeah, you're trying to increase your total energy, so that makes sense. Alright. And then this one's 4.24, very cool. Dang, we missed, like, 2 in the first, like, 3. Okay, that's kind of fun. Alright. Which is the last one? What, this is the last one? What? Wait, I put E? Wait, didn't I say A? Oh, it's showing the correct solution. Wait, I literally put. Oh, I must have missed bubble, dude. What? Well played, well played. All right. I meant to put A, right? Well, why did I put E? I literally didn't use. Okay, whatever. Unfortunate. All right. So which one were we not sure about? we were not sure about number, what was it? Oh, this one. Okay. Okay, so there's a difference of 2 mg due to gravity. Why 2 mg? Oh, it's not magnitude, dude. Wait, is it not magnitude? Wait, hold up. Wait, that's so big brain. Alright, so it's acting. Oh. Wait. Oh, so it's. Oh my god, why am I so. Alright. So this was. Oh. Yeah, okay, that would make sense. I'm so bad. Okay, so this would be MVF L, and the other one would be MV0 squared over L minus mg because it's acting against the tension. No, sorry. Wait, what? No, sorry. The bottom should be mg, so as you increase your mass, it should be more tension, right, at the bottom. So this should be mv f squared over L minus mg. Oh, bro, I'm so bad. Alright, that should have been easy. Okay. And then if you subtract them, then it's just like 4 mg plus mg. Alright, 2 mg. Alright, very cool. Alright, very nice. Alright, that's all I got for you guys today. I hope you guys found that helpful. Thank you guys so much for watching again. As always, if you enjoyed the video, leave a like and subscribe for more. Let me know what else you guys want to see. But other than that, that's all I got for you guys today. So, thank you guys again. So thank you guys again for watching, and see you guys next time.